So, hello everyone. Good afternoon. My name is Rohan, and I think you all come here to look inside Postgres together with me. So, let's get started. So today's agenda, we're going to be starting with Postgres MVCC. Before we get MVCC, we're going to look at what transactions are and how transactions actually behave in Postgres. Right? There's a few nuances to how transactions actually behave. Apart from that, we're going to be taking a deep dive into MVCC, and we'll also be looking at how Postgres stores data physically on disk, how a table is stored on disk, and how actually do reads and write requests take place, right? And at the very end, we're going to look at how MVCC impacts performance and a very special process called vacuum that is going to save us, right? So let's get started. We're going to start with what transactions are, and we're going to do that in Postgres, right? And as all of you know, transactions basically mean all or nothing. You either get everything that a transaction promises, or if something fails along the way, you don't do anything at all. You roll back all the changes, right? And we're going to take a very simple banking example here. It's a classic example. We have two users, Alice and Bob. Alice has 500 and Bob is 200. Let's say you want to transfer 100 from Alice to Bob. You're going to deduct 100 from Alice and add 100 to Bob, right? And this is how you would typically do it. You run two update statements, removing 100 from Alice and incrementing 100 to Bob. Let's say you didn't use a transaction in this case. There is a slight chance that the update statement, the second update statement, could fail after the first one is executed. In that case, you would have your 100 just floating around in air. Alice would lose 100, but Bob would not gain that 100, right? And that is actually not fair, right? It's not fair on part of Alice. But if you actually wrap it inside a transaction, what the transaction guarantees is that you will either commit both of these statements, or if the second statement fails, the transaction would roll back, meaning the 100 is given back to Alice. So Alice would not lose out any money, right? Now to go more into detail on an asset compliant database like Postgres, let's talk about what I in asset is, and that is the isolation in asset. So what does isolation actually mean? It means that if you have more than one transaction running concurrently, or in simpler terms, running at the same time, they shouldn't be interfering with each other. Like if one transaction is doing modifying any state of data, the other transaction should not be affected by it. And let's actually go through some examples here, and we'll actually go through several varying degrees of isolation. And these degrees of isolation is actually chosen per requirement, and we'll actually go through a few of them, right? Now, in this first example, assume you have two transactions running in parallel or concurrently. Transaction 1 and transaction 2. Both the transactions see the same amount of data, that is Alice and Bob. Both are 500. Alice is 500, Bob is 200. Perfect. Now, transaction 1 makes the transaction to move 100 from Alice to Bob. So you would end up with Alice having 400 and Bob having 300. But if you notice in transaction 2, when you do a select, you still see the old data in transaction 2 as was original, right? Transaction 2 still sees Alice having 500 and Bob having 200, even though transaction 1 has modified those. And the reason for that is transaction 1 has not committed its changes yet, and that is why transaction 2 is not seeing the updated value. And once you do a commit, you would actually see the updated changes, right? And this is Postgres working under the hood to prevent something called a dirty read. A dirty read, you call a read as a dirty read when a transaction is able to read uncommitted data from another transaction, right? As you see in this example, transaction 2 was not able to read uncommitted data from transaction 1. So by default, Postgres is preventing a dirty read, right? And this brings us to the varying degrees of isolation levels, and the bare bones isolation level that Postgres provides is read committed. If you read it literally, it means read only committed data. That means you're only going to read data that is committed by transactions. Uncommitted data is not visible to any transactions, right? But some situations call for stricter isolation levels, and we'll take a quick example. We'll look at a quick example of this. Again, coming back to the same example, but let's only look at Alice for now. Now you have Alice, transaction 1 and transaction 2, see that Alice is 500. Transaction 1 wants to remove 100 from Alice, whereas transaction 2 wants to remove 500. Now this is something only one transaction can go through, because if transaction 1 runs first and it removes 100 from Alice, Alice will be left with 400, right? And then if you remove another 500, you'll end up with minus 100. Now let's just go through the flow of what happens here. When transaction 1 first starts the update, Alice's balance is now 400. Now, whenever a transaction does a write operation on a row, or basically when it's updating a row, an explicit write lock is applied. or basically an explicit write lock was acquired by the transaction. And hence you see here that transaction 2 is blocked until transaction 1 commits. Only after transaction 1 commits, transaction 2 can finally do its update statement, and you will end up with Alice having -100, right? And this is an undesirable outcome, right? You definitely don't want negative balances. If definitely not something like a bank, you probably want more stricter regulations on how this is handled, right? And this is what brings us to higher levels of isolations. The first isolation level we saw is that we will only read committed data, but there's no strict regulations about how do we write to the same piece of data modified by other transactions. And there are two sets of isolation levels that Postgres provides additionally, and that is called as repeatable reads and serializable. They both do different things, but commonly what they do is if the transaction detects that the row it's trying to update is already been updated by a concurrent transaction, it is going to reject your update. And this is what will actually happen in reality. If you would apply one of these higher levels of isolation in your transactions, what would happen is when transaction 1 updates Alice and deducts 100, and Alice is left with 400, transaction 2 will wait for the commit on transaction 1 for the lock to be released. And once the lock is released, transaction 2 can go ahead and run its update statement. But if you observe, this will actually result in an error, and the error statement will say could not serialize access due to concurrent update. This basically means that transaction 2, when you run it on a higher level of isolation, detects that the row it's trying to update has actually been updated by a different transaction. And this actually could be unsafe, right? And this is why Postgres will actually reject this update and explicitly call out an error. Usually what you'd want to do is do a retry. Before doing a retry, you'll probably check the balance of Alice first and notice that Alice has 400, and hence you can't really subtract another 500 from it. And this is where a higher level of isolation does come into effect and does help out. And this is exactly what you would do if you were running a bank of your own, right? Some bare bones minimum restrictions around transactions, right? Another thing about repeatable read is that it prevents new data from being visible. Now, what I mean is, in the previous example, we saw that once transaction 1 has committed its data, we do see the updated values in transaction 2, right? Even though transaction 2 is still running, the updated data is visible because transaction 1 has committed it. Now, when you apply a higher level of isolation level, if you notice, transaction 1 has deducted 100 from Alice. It has even committed the transaction, but transaction 2 is running at a higher level of isolation level, and hence you would still see the older values. Right? You'd still see the older value that is 500 instead of 400. And this is what a higher level of isolation gets you in Postgres with the repeatable read and the serializable isolation. And the reason it's called repeatable read is that the reads you perform are actually repeatable. The outcome you get is repeated. In this case, you see a 500 and you again see a 500. The changes applied by concurrent transactions are not really shown here. And hence the outcome is repeated. And hence it's called repeatable read. The interesting bit is, how is Postgres or any modern RDBMS actually doing all this transaction isolation, right? You have multiple transactions running at the same time, modifying data, and then how does Postgres actually figure out, hey, this piece of data is only visible to this transaction, whereas another set of data is visible to a different transaction, right? And this is usually done by some form of concurrency control, and Postgres uses a version of MVCC. MVCC stands for multi-version concurrency control. This is not unique to Postgres. MVCC does exist in other databases and other forms of tooling, but the way Postgres does it is a bit unique, and we'll actually get to internals on how it does it. But on the gist, what Postgres does is, what MVCC does is it maintains multiple versions for the same row, right? What that means is when you do an insert, you end up with one row, but when you do an update, what MVCC will do is, instead of touching the existing row, it's going to make a copy of that row and do the updates on that. So it's going to maintain multiple versions, like version 1, version 2, version 3. And the way it achieves this is it stores a bunch of visibility and versioning metadata at the row level. And we'll actually look at how that looks. And before we go there, as I said, an update will actually translate into the row being copied and then the update taking place on the copied row. And this basically means that writes in Postgres are immutable. Once you write something in Postgres, there's no way you're going to be touching that piece of data again. If you're touching that piece of data again for updating it, you're making a copy of it and then making the changes, right? And these multiple versions, right? These rows have multiple versions of them stored on disk. And these rows and these multiple versions are actually formally called as tuples. So if you do an insert, you would actually end up with one tuple on disk. Whereas if you do an update, the same tuple is replicated or basically duplicated, and then the update is applied. So when you do an insert plus an update, you would end up with two tuples that is on disk. But for the user facing side, you would be shown only a single row. That is the latest row, right? Now let's actually go through a small illustration of how this looks like, right? Now we're back to the same example where we have Alice with 500 and Bob with 200. When you run the first update statement, what Postgres will do is it'll create a new version of Alice. And you can see the balance has been updated from 500 to 400. And it'll mark the old row or the old tuple as dead, or it's going to soft delete it. Basically, someone else will come up in the future to clean it up, right? We'll get to that part in a bit. Similarly for Bob, when you do an update statement, a newer version of this row is appended or basically inserted. And you can see the chain that is formed here. And the older row is marked as dead, or basically it's a soft delete. And the question, again, coming back to the question we asked earlier, right? The first two rows were visible to transaction 2, whereas the bottom two rows were visible to transaction 1. That was actually doing the updates. So different pieces of data are visible to different transactions, right? Now, how is Postgres able to figure that out? Now, this is all in what data the tuples store. And along with the row data, tuples actually store a lot of versioning information, right? And this versioning information is similar to timestamps, where basically you can tell the tuples basically store when they were inserted and when they were deleted. It is sort of similar to timestamp. And this way you can tell how old a tuple is, or what is an age of a tuple. To give you an example, if you insert a tuple at 10 p.m., if you updated it at 11 p.m., you know a transaction running before 11 p.m. will actually see the tuple that is at 10 p.m., right? If you get the sense. So the important thing to note is that the versioning data should actually be comparable. You should be able to compare two tuples and tell which is older and which is newer. And the way Postgres does this is using transaction IDs. Now, every transaction you run, or basically every statement you run in Postgres, every select statement, every write statement, such as an update, insert, or delete, implicitly is run inside a transaction. You don't have to declare a transaction explicitly with the begin clause. Implicitly, all statements are run as a transaction, and all transactions are associated with a transaction ID. This transaction ID is an always increasing integer value, and it is always unique to every transaction. So if you have transaction 1, the next transaction is always going to have an incremented value, that is 2, and then 3, 4, 5, and it goes on. And this is the data that Postgres stores per tuple. A tuple stores which transaction has inserted it and which transaction has deleted it, right? And if you look at the example again here, you can see we have the same example, but we have two additional columns here. I'm calling it created by and deleted by. And created by 750 basically means that transaction ID 750 has inserted the first or created the first tuple, whereas the second tuple was created by transaction 751. And you can see the deleted by is 0. If deleted by is 0, that means the tuple has not been deleted yet. It is still alive or in the live state and can be read by any incoming transactions, right? And let's actually walk through the example again, right? You would do the first update statement to remove 100 from Alice. And in this case, what's going to happen is the transaction that we have started up has an ID of 763. So the new tuple will get a created by as 763. But if you notice, the older tuple gets a deleted by of 763. This basically means that the transaction with the ID 763 has deleted the old tuple, and the new tuples has been inserted in the same transaction, and hence gets the same value. And so on for the second update. We're updating Bob to get 100 more. So similar situation here, where you see created by filled as 763, and the deleted by for the older tuple of Bob having 763, right? And once you commit this data, Postgres will then mark the first two tuples as dead for someone to come and clean it up later. And the columns created by and deleted by just for illustration purposes. But if you want to go with the proper Postgres nomenclature for this, these are actually called xmin and xmax. So created by is basically xmin. Postgres calls it xmin. And deleted by is basically xmax. So xmin is the So xmin column stores the transaction ID that inserted the tuple, and then xmax is the transaction ID that deleted the tuple. And if xmax is 0, that means the tuple is still alive. No transaction has come and deleted it yet. And this should give us a hint on how do transactions decide which tuples they see. And this is actually quite simple, right? One more additional thing to note is tuples will also store if a transaction has committed or aborted. To give you a simple example, if you take the case of Alice, and for an instance, if you assume a transaction 763 has come along and deleted the first tuple, but has not committed, and that means it's aborted, the transaction has been aborted, that means it is ideally still visible. The newer version should not be visible because the transaction has been aborted, right? So tuples will actually also store whether the xmin and xmax transactions are committed or aborted. And these are some of the these are simplified conditions on how do you decide whether a tuple is visible within a transaction or not, right? The very first condition is that xmin has to be committed, right? If you have xmin committed, that means you know that the tuple exists. That's actually alive and can be read. And another way you can, and the follow-up condition for that is xmax should be equal to 0. That means the tuple is live and not deleted by another concurrent transaction, right? In case your xmax is not 0, the only way the tuple can then be seen is when xmax has not been committed, right? Let's say a transaction has come along and deleted a tuple, but has aborted the transaction. That way, your tuple can tell you that whether xmax is committed or not. And if it's not committed, you can basically ignore the xmax value or even consider it as 0. And this example is, and these conditions are for the read committed isolation level. Whereas if you look at any of the higher isolation level, we said that any new data is not visible in those transactions, right? Even if another transaction commits new data, the transaction with running at a higher level of isolation level will not see that new data, right? And the condition for that is quite simple. For the transaction running at a higher isolation level to see data, to basically not see any incoming data, the condition is that the tuple xmin value should be lesser than the current transaction ID. That means that transaction is only seeing all the tuples that have been inserted previously of its run. And that's where this condition only applies to higher isolation levels, right? This is a small snippet. You can actually query the statistics table in Postgres. The table name goes by pgstat all tables to give you the count of number of live and dead tuples. And you can see here, the number of live tuples is 2, number of dead tuples is 2. That's because we did 2 updates, and that will result in 2 tuples being added and the previous 2 tuples being marked as dead. Let's talk about indexes, right? As we said, one thing to know about indexes is that indexes always point to the physical location of a tuple on disk. Now, the concerning bit is when you update a row, a new tuple is being inserted, and its physical location is different than the original tuple. Now, what actually happens to the index? Does the index still point to the older tuple, or will the index actually point to a newer one, right? And to understand this, first we have to understand what is the tuple's physical location on disk. And let's actually see how a tuple is actually stored on disk. And before we even get to a tuple, we'll actually look at how a table is stored on disk in Postgres, right? There's a small graphic right there. So a table in Postgres is stored as a single large file, provided that the table is less than 1 GB. If the table is greater than 1 GB, Postgres will ensure to use multiple files to represent that table. But in our example, assume we have a table that is less than 1 GB. It is stored as a single large file on disk. And this large file is again split into smaller fixed data blocks called pages. And each page is of 8 kilobytes. And these pages are the ones that will house the tuples. This is analogous to virtual memory, where, or basically an OS file, where a file is broken down into multiple pages, and then those pages are actually stored on disk, right? This is analogous to that. And here you can see that the pages inside the table are actually the ones that house the tuples, right? The pages contain some metadata or headers along with the tuples is going to store. And these tuples are storing the actual table data, such as the rows and columns. There exist other types of pages as well that store other pieces of information. For example, your indexes, such as your B tree indexes, are stored in different types of pages, and those are called index pages. What you're seeing here is called a heap page. A heap page is something that stores the actual rows and columns of a table. That is the actual table data. And one thing to note is that pages always start from 0, and as a page gets full, you're gonna keep adding new pages into the table, right? And this brings us to how do you determine a tuple's location, right? And it's actually quite simple. A tuple's location is basically made up of two numbers. The first number denotes which page it lies in. The second number denotes where in the page does the tuple lie. And this is actually called offset, or formally Postgres calls as line pointer, which is same as offset. So for example, 0, 3, if a tuple has a location of 0, 3, that means it lies in page 0 and offset 3. And the location of a tuple is actually called as tuple ID, or is sometimes represented as CTID. And the beautiful part about this is you can actually query a table to give you its CTID, Xmin, and Xmax. As you can see in this example, we can see that Alice's updated tuple lies at 0, 3, which means that this tuple lies in page 0 and offset 3. As you can see for Bob, it's at 0, 4, which means this tuple lies at 0th page and offset 4. And the corresponding Xmin and Xmax values. The Xmax is 0, stating that these tuples are alive and not dead. Let's actually come back to indexes. Now we know what the physical location of a tuple is, and we know that indexes always point to a tuple's physical location. Let's actually see what happens when you do an update, because when you do an update, you're adding a new tuple. Now, what actually happens to an index when you do this? In this graphic, you can see the actual data columns are ID, name, and balance. Assume we have a single row, ID of 1, name of John, and a balance of 6,000. And these are the metadata columns, such as your offset, or also called as LP, line pointer. You have the tuple's location, that is 0, 4. That means John with 6,000 balance, that tuple lives in the 0th page at offset 4. And this tuple is alive because the Xmax is 0. And you can assume Xmin is committed for this. And you can see that the index of ID 1 is actually pointing to 0, 4 here. It's actually pointing to the physical location of the tuple at 0, 4. When you do an update statement, when you're updating John's balance to 8,000, you're going to insert a brand new tuple. That's the way MVCC works in Postgres, right? Now, you can assume that, now one thing to note is indexes in Postgres are actually immutable as well. That means you cannot update an index in place. You're going to actually make a new entry for an index and mark the old entry as dead. Similar to how tuples work, indexes also follow a similar fashion where a new index is inserted. And this new index is pointing to the new location of the tuple, that is 0, 5. You can see the older one is marked as dead, and the new index entry has been made to point to the new tuple that's inserted at 0, 5. And you can see the older tuple Xmax value has been set to 764 because that's the transaction that deleted it, and 764 is the one that inserted the new tuple. But the thing is, this is not actually what happens under the hood. This is actually not done in Postgres due to something called as heap only tuples, right? And before I explain the term heap only tuples, let's see what Postgres actually does. And this is an optimization Postgres does. Now, the first thing to understand is that updating an index in Postgres is extremely expensive. So what Postgres will do is try to avoid an index entry, or basically updating the index in any means as possible. And what Postgres does here is it updates it when you run the update statement, it definitely does insert a new tuple. The new tuple is at 0, 5. Now what it does is it modifies the old tuple CTID value from 0, 4 to 0, 5. Now this is done because the CTID column actually has two purposes. The first purpose is to point to the tuple's physical location. The second purpose of the CTID column is that if there exists a newer version of the tuple, the value will point to the newer version. So in this case, since the second tuple is the newer version, the CTID value of the old tuple has been changed to redirect to the new tuple. And you can see in this sort of the arrows pointed, the index points to the old tuple. The old tuple will then say, hey, go redirect to a newer tuple that exists at 0, 5. And you can see this sort of forms a linked list, or basically a chain. It's typically called a hot chain. And the name heap only tuples is given because it's not updating the index, but only the heap. Now, as I said, the pages that store the actual tuples and the rows is called the heap page. And that's why it's only called heap only tuples. That means only the heap tuples are modified. The index pages are not touched in this case. Now, again, moving along with the chain, if you have another update for the same row, you would add another tuple due to MVCC, and then the older tuple CTID value would change from 0, 5 to 0, 6. So the linked list will move on. So it starts from the index and then goes along. And this is how, and now if you perform an index scan, this is how it would look. You would start with the index. The index would point to the oldest version of the tuple. The oldest version will point to a newer version and so on. And so when you do an index scan, you're actually not directly hitting the index, and then the index is not taking you to the latest tuple. But what you're doing is you're walking the linked list along with a chain of tuples that will eventually get you to the latest tuple, right? Sorry? Tuple 1 gets garbage collected. We'll talk about that in a bit, okay? V1 has no idea that V3 has been inserted. Only V2 has an idea that only V2 will know that a newer version called V3 has been inserted. There is another step. What you're saying is another optimization Postgres does, but that is actually a bit later, and it has a few conditions to it. Let's not talk about that for now. But if you're doing an index scan, you're going to walk from the index all the way from the oldest tuple all the way to the newest tuple. So you're walking the linked list all the way. And this chain can get quite big. Yeah.
So when there's a long running read transaction, does it have to walk the linked list from the oldest to the newest?
If Postgres chooses to do a hot update for all of the updates, then yeah, you will have to walk through all of them, unless something comes along and cleans it up, which we'll talk about later.
Okay. So if you're updating the CTID, how do I know what was, and I'm doing repeatable reads, how do I know which version I have to read? I'm doing repeatable reads.
Okay, so that is purely based on the xmin and xmax columns.
Okay, not the CTID. Got it.
Right. So if you have an xmin, let's say 770, with the repeatable read isolation level, you would not read the third tuple. You would stop at the second tuple, right? So that's how the isolation level will impact this. And this is, if you're doing a sequential scan, the head of the linked list would actually change to tuple v1, because if you're doing a sequential scan, you would not start from the index, but you would start from the pages. That is you would go through all the tuples one by one, and then you would walk through the linked list of versions all the way from tuple v1 to v3. Before we talk about heap-only tuples, there's actually an extension in Postgres called page inspect. It literally means that you can inspect a page on disk and how it looks. And this extension gives you a bunch of handy functions to do that. And let's actually look at this example, how it looks on disk. Like when you actually inspect the tuples, the raw tuples, and the raw pages, what would you actually get? And you can see that there is a hot update here. The index is pointing to tuple 1 at line pointer 1, and then line pointer 1 is redirecting to line pointer 2, right? Now we're going to look at the index first, and the function I'm using is bt underscore page underscore items. This basically says that get me the B tree from this page, and my index is called accounts underscore p key because it's a primary key. That's why the name as p key. And I'm looking at the page 1. I said pages start from 0, but in case of indexes, the 0th page is reserved for metadata. So the B tree index will actually start from page 1. And interestingly, you can see I did a select star, but the interesting columns for us are CTID and data. The data column is the one that stores the index value. That is this ID key. This ID is our primary key where the B tree index sits on. And this ID value is actually stored in the data column and is stored in a hexadecimal format. So Postgres will actually decode that. And if you actually look at this actually represents the value 1. And the index also has the value CTID, the tuple it points to. And in this case, it's pointing to 0, 1. So index value of 1 is pointing to the tuple at 0, 1, right? Let's actually look at the tuples now. And you'd use a different function for this. And the function called as get raw page, you're actually getting the raw page of the accounts table of page 0. Remember we said pages start from 0. And then we're telling Postgres that render it as a heap page. You can actually query a lot of different types of pages, but in this case, we're interested in looking at the heap page. And the interesting bit is that you see two tuples here, line pointer 1 and line pointer 2. And the tuple at line pointer 1 is redirecting to line pointer 2. But if you look at the previous one, the index is pointing to line pointer 1, and line pointer 1 is redirected to line pointer 2. So this is actually evident when you inspect the pages on disk that the heap-only tuple optimization applies here, where you start from the linked list, where you start at the head of the linked list as the index, and then go to the older version at line pointer 1, and then line pointer 1 will redirect you to line pointer 2, as you can see here. There are two interesting more columns you are seeing when you inspect the raw page. The first one is t underscore data. This is how the tuple is actually stored on disk. Again, this is a hexadecimal format. All the columns such as CTID, XMIN, XMAX are all coming from this piece of information. You decode this hexadecimal string, you're going to end up getting all these columns along with the row data. That is the ID, name, and balance columns. All of it comes from this representation right here, and this is how it is stored in pages as a raw format. The LP flag is a bit of an interesting. We'll come to it again in a bit, but basically the LP flags column marks the state of the tuple, whether it's dead, alive, or more states that we'll look at later. In this case, LP flag of value 1 means that the tuple is still alive. It's basically equals to normal. Normal means the tuple is live and it can be read. Now, as we said, when for a heap poly tuple optimization or a hot update to occur, there are a few conditions, and we'll actually look at these conditions in detail. The first one is the index field is not supposed to be updated, right? If you don't update the index, a heap poly tuple optimization can happen. And the second condition is when you update an older tuple, a new tuple has to be inserted, and a hot update can only occur if the new tuple falls in the same page as the old tuple, right? And we'll actually look at why this is the case. Let's start with condition 1. Let's say you're updating the index value. You would not rely on the hot update, right? And this actually makes sense because for this example, we have an index on the email field, right? And you can see the index email john@abc.co is pointing to tuple 0,4. And when you do an update, you would end up with a new tuple. But this time I'm actually updating the index value itself. The email field is actually updated. So you would see that in this case, it makes sense to update the index because you're updating the index column itself and the index has to be updated. So in this case, you would not see a redirect. Postgres will actually construct that new index entry and it will point it to the new tuple. Now you will still see that the CTID of the old tuple has been modified to redirect to the new one, and this is for sequential scans because an index scan would be going from the index all the way to the newer tuple, whereas a sequential scan will be walking a page. So you'll come from top to bottom and you'd expect the redirection to help you search much faster. Now the second situation is when the updated tuple lies in a completely different page. As you can see in this example, we did an update and the tuple actually landed in page 3. The first tuple is in page 0, but the new tuple is in page 3. And in this situation also, Postgres will actually go ahead and take that expensive index update operation. And you can see a new index entry has been inserted to point to the new tuple that is in a completely different page. And again, you can see the older CTID value has been changed to reflect the update. And again, this is for sequential scans. But there's a reason why Postgres takes the extra effort to update the index when the newer tuple falls in a different page. And there's a reason for this. And the reason actually lies in how Postgres reads and writes data, or how it serves read and write requests, the architecture behind this. And for that, we have to understand how the read and write mechanism works in Postgres. Now, the thing to note that is all the tables and the pages and tuples are all stored on disk, right? And for Postgres to do any such operations on them, any operation on a page first has to be loaded up in memory for a read or write request. And this memory is called as shared buffers, and it is a limited set of memory. Now, the concept here is that if the page doesn't exist in memory, because the memory is limited, you'll be shuffling pages back and forth from disk into memory, you will encounter page faults. If the page is not there in the shared buffers, you will actually have to load the page from disk, which is a very expensive operation again, and will increase your response time, and that is called a page fault. And the reason why Postgres calls this as shared buffers is Postgres has multiple processes or background workers running parallelly, and all of these background workers use the same piece of memory, and that is hence the word shared buffers. The memory is being shared by all of the workers, right? Here's a simplified version of how a Postgres read-write mechanism works. Let's start from the left to the right. You have an incoming request, and the background worker in Postgres will pick up your request to operate on it. Now, for anything for the worker to do a read or a write, the page has to be present in the shared buffers, right? So it checks if the page is present. If the page is not present, it's an expensive operation for it. It's an expensive operation to load it from disk into memory, right? And so that would result in a page fault. It's analogous to how virtual memory page faults work. It works pretty much the same. And once the page is loaded into the shared buffers, the background worker can actually update the page in case if it's a read. If it's a write, the background worker updates the page. It marks the page as a dirty page, which is then flushed back to disk at a later point of time. If it's just a read, the background worker just reads the page and sends the response back to the user. And the page will then get shuffled back into disk if due to limited memory or access patterns. There's also the wall. Whenever you get a write, you log the changes into a write ahead log, but let's not go into this right now. And if you can observe why we don't have a heap only tuple update across multiple pages, and the reason for that is quite simple. If you do a redirection, or if you build a linked list from the index that redirects to multiple tuples across pages, you'd be loading a lot more pages from disk into shared buffers. To take an example, if your index points to page 0 first, you'd load the index page and then page 0, the heap page 0 into the shared buffers. And if the pointer from page 0 points to page 3, you would also end up having to load the page 3 from the disk into shared buffers. So if you end up doing a chain across pages, or basically a linked list across pages on an index scan, you would end up loading more pages from disk into memory, and that will lead to more page faults. And that's exactly what is written down here. And basically, you would want to avoid page faults, or basically keep them as low as possible in order to get better performance out of your Postgres server. And having fewer pages also matter in Postgres, right? And this matters because your shared buffers, or the cache, is actually a limited set of memory. And the fewer pages you have, the less amount of memory you'll have to use in that, right? And this is actually a problem for us because Postgres uses MVCC for transaction isolation, but MVCC is also creating a lot of dead tuples, a lot of junk, you would call, right? Update statement generate a new tuple. There's data duplication happening. The older tuples take up storage space. The newer tuples are taking up storage space, and that will lead to more pages being created as long. There's a small graphic to illustrate this. Assume there are page 0 and page 1, and assume for now, for the sake of this illustration, that a page can only store 5 tuples. In this case, if you get an insert, the newer tuple will have to actually go into a new page, that is page 2. And this will increase the number of pages you have for the table, and that would lead to more possible page faults in the future, leading to more response time or higher response time. Now the thing is, how do you actually reuse some of this dead space, right? This is a dead space. It's basically junk, which is not used by any transaction, right? It's safe to assume that after a point of time, no transaction would need to look at such dead tuples, right? And this is where you'd have the concept of vacuum. Vacuum is basically like your garbage collector that comes along and says, hey, these tuples are basically useless right now, so I'm going to get rid of them. So the space there can be reused. But the important thing to note here is that vacuum doesn't delete the tuples. It only marks the tuples as dead, and it only checks the dead tuples as reusable. That means the space the dead tuple is occupying can be overridden with new data. It doesn't actually release the storage from Postgres into OS. Now, to give you an example how this works is the same example. Before you do a vacuum and after you do a vacuum, what happens is the dead spaces are marked as reusable. The data is not deleted. The data still exists. But remember, we talked about the LP flags column. That flag is changed to tell Postgres that, hey, these tuples are now reusable. If you have an incoming write, you can reuse the space that was once held by a dead tuple. And this is how vacuum actually helps us reclaim some of that space indirectly, because you're not claiming the storage space directly, but it's being reused, or data is being overridden on those places. And this helps you keeping the number of pages to a lesser amount or a lesser count. And again, there's a note here saying that it only marks them as reusable. It doesn't actually free up storage space. And to give you a more in-depth explanation or an example, let's look at this example. We insert 1 million rows. That means you end up with 1 million tuples. Assume the 1 million tuples take up 71 MB of storage. If you update the 1 million rows, you would end up with 2 million tuples, right? Because an update will generate a new insert, and that will end up with 2 million tuples. 1 million of them, 1 million are dead, whereas 1 million are alive. And the storage space would actually double because the tuples actually take up storage space. If you run vacuum, you would actually see no difference here because, as we said, vacuum will only mark it as reusable, not actually clear the space. But notice when you do another update, you would expect another set of 1 million tuples to be inserted, but the overall tuples in the table remains as 2 million. That's because vacuum set the 1 million dead tuples as reusable, and the update statement that got in 1 million more tuples are actually reusing that space. And hence your storage space or your table storage doesn't increase, it remains the same. There is another thing we didn't discuss, and that is an extension to vacuum. It's called vacuum full. It's another command you can run in Postgres. Vacuum full, what it does, it directly frees up storage space on a table. Instead of just marking dead tuples as reusable, it actually goes and clears up the space and compacts the pages. And in this case, if you run a vacuum full, you would actually end up having only 1 million tuples, clearing up all the dead tuples, and the storage space brought down to just 71 MB. Right. A bit of note about vacuum full. The way it works is vacuum full is a very expensive or a very compute heavy process. What it does is it takes your table and creates a completely new file by compacting all the tuples inside the table. So basically, you're not just operating on the existing table file, but vacuum full will actually create a copy and then compact all the things in there. It's basically rebuilding the table from scratch, and that way you end up by compacting all the tuples in there by removing all the dead ones. And one thing to note is that the regular vacuum process is run automatically by Postgres on a few triggers, and the triggers are quite often. Vacuum full is not run as an automatic process. This is due to some of the few caveats vacuum full has. And the biggest caveat is that vacuum fill actually locks your entire table, so no reads or writes are allowed into the table at all, right? And again, as I said, it uses a lot of resources, and it's preferably to be never run. Now, what do you do in such cases where you would actually need immediate disk space, right? In those situations where you would need immediate disk space and application downtime is acceptable, you would run vacuum full, but there are other ways to run it, such as you would run it on a replica first and then make that replica as a leader and etc. And then continue running it on the other replicas. Another alternative is to use an extension written by the community called as PG repack. It does exactly what vacuum full does, but it's a bit more forgiving, where it doesn't lock the entire table. It locks sections of the table incrementally. So that's much better than having to lock the entire table for a long amount of time. Yeah, that we have come to the end of this talk. A few references and any questions? Yeah. Sorry?
Does Postgres allow a tuple to span more than one page?
Yes, it does. So as we said here, a page is of only, where is this? A page is of only 8 kilobytes. And let's say you have a very big, each row exceeds 8 kilobytes, Postgres will actually split the tuple into multiple pages. It's actually called toasting. The term uses toasting. So Postgres will toast the tuple into multiple pages.
But those toast columns are like stored separately somewhere.
Yes, the tuple is physically split into multiple pages, and metadata will ensure to reconnect them later.
Okay. How does vacuuming work in that cases?
Again, your metadata will tell you which parts of the page contain parts of the dead tuples, and you'll only vacuum those sections, right? And there's actually something like a flag you can look out for if your tuple size exceeds 8 kilobytes. That is something you could work on optimizing your database. Or another extreme thing you can do is the 8 kilobyte page size is actually not changeable. In Postgres, you cannot, but in other databases such as Oracle DB, I'm assuming some of the enterprise databases, you can set page sizes per tables. In Postgres, that's not possible, but other databases do offer that feature. If you want to change the page size in Postgres, you'll have to recompile Postgres and then change the config over there while recompiling it. Yeah. Yes. Sorry? I would assume it would work the same, where the tuple, it would point to some part of the tuple in one of the pages, right? It would point probably to the starting point of the tuple in one of the pages. And then the tuple would be reconstructed and then the index would point to that. I'm assuming that's what happens. I've not really looked into that aspect yet. Yeah. So when an insert is coming in, it'll obviously look to insert into an existing page rather than creating a new one. And there are some algorithms based on how efficient it is to load a page from disk. I haven't really looked into that, but you can assume that it'll look for a page where space is available first, right? And there are some edge cases where it'll actually go and create a new page altogether. There are some resources around that I mentioned here, so that's probably could come in handy.
Yeah. So let's say I run a bulk migration. So I'm adding a new column with a default value. So does Postgres create a tuple and proceed, or how does it happen? So here we have seen updates, but let's say I'm inserting a new column. I want a new column in my table.
Oh, okay. That's interesting. Yeah, I would assume because every write is immutable in Postgres. So I'm assuming that Postgres will actually make a new copy of that when you're adding a new column altogether. Because the underlying data cannot be changed. So it only have to make a copy and then add the new column. I'd assume that's what would happen. I've not checked that, but that's an interesting thing to check actually.
Okay.
You mean the T underscore? Yeah, T underscore data. This is the raw structure what the tuple is stored. Obviously, if your data changes, the hexadecimal string will also change. Yeah, that should be a concern. Oh. Hmm.
That only then it doesn't actually take a table lock or rewrite the entire table for the new columns. Whenever let's say if there are some operation which takes entire table rewrite, then it takes from metadata and rewrites the entire table. It doesn't touch it. Like if you add a 1 TB table, you can add a new column. It doesn't lock it. It finishes it in milliseconds.
Question. Hello. Yeah. So you said the index is immediately updated during updates. So now if there is a read transaction going on, it's going to check the index, but does it have to look at the page to figure out that this index update is not for me?
I didn't get that.
So the index is being immediately updated, right?
In which case, when you don't have a hot update?
When you have a hot update.
When you have a hot update, index is not updated.
Okay, I mean the other way around, sorry. No hot update.
Something like this, where you...
The next one, no hot update.
Yeah, this is not a hot update. A new index entry has been added here.
Right. So now if there is a read transaction going on in parallel, it's going to look at the index and then it has to again look at the page to figure out that the xmin, xmax is not for me. So it should not be reading dirty indexes.
So indexes don't actually use xmin and xmax. While writing to an index, a lock is acquired explicitly for that. So that's why updating an index is way more expensive, because they have a different way of mechanism for versioning, which involves locks.
Okay. No, I meant like, does the read transaction look at the index also?
Read transaction as in?
I mean, somebody's doing
okay.
reads. Somebody's doing reads. Like I want to do a select distinct on all the email values. Will I be looking at the index on the next page?
This one.
Yeah. Then I'm sorry. If you can go to the next slide. The next slide. There was something about emails.
But to answer your question, if the index is committed, or basically the index persists, then based on the isolation level, in the read committed, you would definitely look at the latest index.
Okay, we'll take it offline. All right.
Yes, it has to be in the same page. That's when it would go to a different page, and that's what you're seeing right here, where you would actually add an index entry if the tuple goes to a new page. A new index entry has been added if the tuple goes to a new page.